What's going on, guys? It's the Unhinged Engineer here, back today with a technical video. That said, a pretty simple technical video, and I want to talk about PID control, which if you're interested in control systems at all, I am very confident that you've heard of it before. When you learn about it in school, you do weird stuff like Potts transforms and root locus methods and all this other fluffy theoretical math crap that overcomplicates something that's actually really simple, really straightforward, and that's the reason it's used so ubiquitously in industry. And so I thought it'd be really good to go over it at a high level, just as you get into classes or actually implementing one for work. You just understand at a high level what you're trying to accomplish with a PID controller and how it works. That's what we're going to talk about today. Like I said, I'm the Unhinged Engineer. I make professional development content for STEM engineering professionals like myself, kind of learning how to navigate themselves throughout their career. On occasion, I also make technical stuff like we're going to do today. So let's get right into PID control. It stands for proportional, integral, and derivative. So what this is a controller. Right, here, let me use red. The PID is a type of controller. The thing we're trying to control here is error. Put simply, we have some desired variable and we have some actual variable. And we're trying to drive this usually to 0, right? So that's where you get these plots, as you will see in this video, where we have this starting point, x of a, and this destination point, this desired set point, x of d, and we're trying to make it so that xa equals xd. Okay, this is like in general what a control system does. We're going to get more in detail about this graph and everything in a second, right? The components of a PID controller are again, really straightforward. We have some method of measuring error, right? And then we have a constant that is proportional to that error. This is called a gain, right? So this is one of 3 gains. So Kp is gain, and then epsilon is error again. There's another one, Ki, that is multiplied by the integral of error over time. Sorry, I'm getting smushed here, but error over time. So we integrate our error over time, and then we multiply it by some constant k sub I. Right? And then lastly, we have k sub d, which is multiplied by the derivative of error with respect to time. Okay? How we compute our errors, we'll get to in a minute, but the main idea here is by designing a PID controller, what we're effectively doing is just changing these gains, which are just constant values, they're just numbers, that we multiply by the error itself, the integral of the error, or the derivative of the error, okay? And the way, like the values of these different controllers relative to one another is what's going to determine the behavior of this control system that's trying to minimize the set point. This is like general control system stuff. Now I want to actually start getting into what these specific things mean. Right, what these specific gains are for. So here, I'll just write out the PID formula again at the top. So that's our PID controller, right? And we have these gains, which we're going to talk about now. So now let's say we have this big graph we just talked about, right? Where this is our value x that we're interested in controlling, and this is time, right? So we're running this control system over time to try to drive our system towards some desired state. So like an easy example, this is altitude. Let's say we have a little drone, and we're trying to fly it up to a certain altitude. And it's gonna start at 0. So at our 0th time step, this error is going to be like just equal to the desired value because x sub a is 0, right? And so what's gonna happen is we're gonna say, okay, the input to our system, we're gonna multiply by that error, right? It's proportional to the error, I should say, right? And so at first, it's going to be really big. So we're going to like slam our thrusters and go up really high, right? And now, this is, our next time step. This error is less than it was before. So this is good. So we're going to go up again, maybe at a slower rate than before because that error is smaller. And then again, and again, until what inevitably is going to happen is we're going to overshoot. So we've minimized this error. We've driven this subtraction, this difference, down to 0, and we've hit our set point, which is great. But now, our thrust is slamming, and we're going to pass through it, right? So what's going to happen? Well, it's going to turn around and come back down, right? So again, it's measuring error here, right? And it's trying to minimize that, and it's going to keep overshooting. like this. And based on like the frequency of your system and how strong this gain is, excuse me, K sub P, we're just gonna oscillate about that set point. Now, if this is really tight, that might be okay, but we can do better than this, right? Like we can have a system that actually converges. So this isn't gonna converge, it's just gonna kind of oscillate around the set point, if we're lucky, for reasons we'll get to shortly. So this is not ideal. So over time, we want it to converge to the set point, right? So what do we add in here? Well, why don't we add not just a proportional term, but also a derivative term. So we're going a little bit out of order here. So we've done the P term, now we're doing the D term. So now let's say we've got, we've got our error. Our error is smaller here, right? So error 2 is less than error 1 is less than error 0, right? So this is backwards, but you know what I'm saying? Like over time, the rate of change is less than 0, right? So we're multiplying this term to say, okay, I'm trying to also drive the rate of change of error down to 0. And now what's gonna happen is, we're gonna say, well, okay, smaller, 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 smaller. And now we're gonna overshoot a little bit. But on the next way down, what's happening is it's saying, okay, look, like right here, the derivative of our error is equal to 0 because it's flat, it's hump, right? And now it's starting to increase again, right? So the rate of change of our error is starting to increase again, right? The magnitude, I should say. And so it's saying, oh, this is bad. Let me start to slow down how much I'm controlling, right? How much control, thrust, whatever we're putting into the system. And so at this point, it's going to turn around sooner. Apologize for my crappy drawings, but you get the point, right? Because I'm measuring not just the error itself directly, but also the rate of change of the error. At each one of these, it's going to overshoot a little bit less each time. And so that's why the derivative term helps you actually converge on the set point. Obviously, there will always be these little oscillations, but eventually your steady state will drive towards the set point. In theory, a PD controller should be enough. And a lot of times it actually is, but sometimes we need this integral term. It does complicate things with like how you store your integral and an integral windup in certain applications, but we're not going to talk about that in the course of the video. So the integral term is actually kind of the last one we add, usually for the most part, right? Because if we don't need it, we avoid it. But sometimes, let's just say for argument's sake, right? We mounted a motor wrong on our drone, or like, a resistor in the circuit that leads to the motor is busted and it's not getting as much voltage as we anticipate. Something weird is going on that makes it so that the control we're putting into the system doesn't actually match what's manifesting in the real world. What might happen is, with just a purely PD controller, you might actually converge to the wrong set point. So again, the magnitude of our oscillations are going down, and we're trying to drive our error to 0. We're trying to do that. But for this weird reason that we might not know ahead of time, like weird with thrusters, propellers, excuse me, we get this steady state error, right? And so at each step in time, if we integrate this, the area under this curve is getting larger and larger and larger. So that's how we account for this like steady state bias, this steady state error, commonly referred to as bias. And that's what the integral term it does, right? So now again, the integral here is getting higher and higher and higher. So if we have something proportional to this area under the curve, and we're also trying to drive that area under the curve down to 0, then that's exactly what's going to happen. We're going to converge to probably look a little bit different from that, but you get the idea that it's going to force this area under the curve down to 0, okay? And so this is how a PID controller works. There's 3 gains that we multiply by the error, so proportional to the error, the integral of the error over time, and the derivative of error. This is all a PID controller is. That's it. There's analog PID controllers that literally wire this out in circuits, so no code required, right? We can implement code, obviously, which is a discretization of the system. I drew it as like a continuous signal. I'm getting ahead of myself, right? One last point I do want to touch on here is how the heck do we implement this? So taking integrals and derivatives of things is hard, especially when this is a complicated physical system with dynamics and, you know, control models, like how our actual input, how much we spin the propellers manifests as altitude of the drone, right? If these are complicated physics, like taking a derivative of things or an integral is not trivial. We take the dumb, obvious route. You just say dE dt equals error. The derivative is equal to t plus 1, error times t plus 1 minus error times t. Okay, I guess technically it should be t and t minus 1. Usually you would do some kind of moving average of that derivative, so it's not like super noisy, obviously. But in like concept, this is it. We're just taking differences in our measurements. And then our integral, how do we do that? We set integral equals 0, and then we say, you know, for t in time, number of time steps, integral plus equals error at that time. You just add the error over and over and over again. And if you're a hardcore computer science, you're screaming at this right now, because I know there's precision issues if the number gets too big, right? But all of this is to say, you're just having an accumulator, summing it over each time step, right? So at that point, it gets really straightforward. Right? You measure the error with your sensors or whatever the hell else you use. You add that error to your accumulator, that's your integral, and then you subtract it from your previous time step, and you're good to go for your derivative. That's basically it, okay? And so, obviously this is a gigantic oversimplification. You've got stuff like Laplace transforms and root locus method and Bode plots and the things I discussed earlier. For the most part, those are related to how we tune these controllers, right? So obviously, how we select these gains is a much more complicated problem. And when you get into PID controller design, that's the kind of stuff you learn. That could be a topic of another video, but to just start you off of saying like, oh, like I've heard of PID controller. What WTF is that? That's the title of the video. This is really like as simple as it gets. We have the proportional term that's driving our error towards 0, so it's forcing our system to go towards the set point. At that point, it's kind of going to bang, like oscillate about it. And so the derivative dampens those oscillations over time. So it scrunches things down and it makes it converge on the set point. And then the integral makes sure any bias and how our model is different from the actual real system, any bias in there, it ultimately is factored out, and you really can be confident that you're converging on the set point you set in the very beginning, which is ultimately what we're trying to do with the control system. Yeah, PID control is something I really like. It's like I said in the beginning, it's the first type of controller I learned before you get off to fancier stuff like LQR or whatever else. But it's in a lot of ways, it's the industry standard. If it ain't broke, don't fix it. Yeah, so I hope this is valuable to you. I hope you enjoyed the video. Like I said in the beginning, I'm the unhinged engineer. I make professional development content for engineers like myself. So the majority of my content is not really technical, but on occasion I do make kind of high-level overviews of engineering concepts I think are of interest to a lot of people, like PID control. So yeah, if that's something you're interested in, or you're interested in my grad school vlog, so I'm getting my degree in computer science at night at Georgia Tech. If you're interested in either of those things, then I highly recommend you subscribe to the channel. This is the place for you. Thank you so much for watching, and I will see you in the next video.